It's my pleasure to introduce Jon Pakianathan from the University of Rochester, and today he'll be telling us about tessellations of surfaces from finite groups. Thanks so much, Jon.
Well, thank you. Thank you to the organizers, Sarah and Henry, for inviting me to speak in this conference series. Today, I would like to talk about some joint work with Mark Herman at the University of Rochester that was actually done a couple of years ago, but I haven't had much opportunity to talk about it, so I'm going to talk about it here. Also, I have to apologize in advance. I'm not quite the highest applied math quotient, but there are some applications that I'll try to outline. So basically, today's talk will concentrate mostly on tessellations. Tessellations, roughly speaking, are subdivisions of a space, often like the plane or 3 space or Euclidean space in general, into cells, where the cells sort of together exhaustively cover the space and intersect in sets of measures 0. That would be the analysis sort of definition. Topologically, the cell structures we'll often look at, and today's talk will concentrate primarily on, will be CW structures, so where the top dimensional cells are the cells in the structure, and we'll talk more about that as we go on. Traditionally, of course, there's been a lot of work in regular cell structures on the plane, from studying crystals in a lattice, so crystal layouts in 3D material science, biological cell layouts, layouts in various chemical molecules. So you'll see if you look up tessellations, a large literature in material science, biology, and chemistry. Unfortunately, I won't be talking much about that today, so mostly I'm going to be talking about the mathematics side. So basically today I want to lay out a sort of construction that came out of work of Mark and I in a different area in math 2 years ago, that associates to the multiplication group of multiplication table of a finite group, a series of surfaces uniquely from that with these nice tessellations on them. And so we'll be discussing how that works. And when we did this, we got a lot of good feedback from the large group of people working in this area, and found that there was many different languages that sort of are used in discussing this. So I'll try to, summarize that a bit as we go through. So just to start off, sorry, I should put this up here. I'll give us some history on the sort of tessellation literature that's relevant for today's talk. And then mostly we'll be talking about cell structures on surfaces. So you might view these as CW structures that are relatively nice, as we'll see going forward. And today we'll be talking mostly about structures that are regular, or what's called dual quasi-regular, which I'll explain in a bit. And when we discuss this, we require this regularity only on a combinatorial level that I'll explain later. So it doesn't have to be geometrically regular. So this would cover a lot of cell layouts on the skin and so forth, things like that too. All right. And then after discussing the background, we'll discuss this sort of construction that associates to a finite group these sort of regular surfaces, basically encoding its multiplication table, or at least part of it. And that will be the second half of the talk. All right. So just as a background, there's been, of course, a long successful history in associating topological or geometric objects to algebraic or combinatorial ones that in order to help study them. One of the first examples of this was, of course, work of Cayley, using Cayley graphs to encode information about the group structure. So to any finite group G and generating set S for the group, you can make a Cayley graph from it. I'm not going to be using these much today, so I just wanted to mention them as one of the early examples of associating a topological thing to an algebraic one to help study it. Other examples more recently in history have been things like the classifying space of a group or the poset complex of a poset. Both of these are special cases of a sort of classifying space for a small category. So basically, this construction can be done on a very general level for any small category, and the space that you get encodes a lot of properties that category has. Again, today we'll keep things down on a more concrete level, but in some sense, the work was motivated by part of the complex BG, as we'll see later. These complexes or geometries associated groups were very important in the classification of finite simple groups. It helped construct some of them and help sort of study simple groups in general, and also currently very important in computations of what's called group cohomology. So it's still used quite a bit. And the geometries have expanded, so you'll see a lot of poset geometry in the area of algebraic combinatorics. So all of these are examples of topological things helping out study combinatorial things. In this talk, when we talk about surfaces, they'll always be closed, orientable, and connected. So they'll therefore be classified just by the genus, which is a non-negative integer. And of course, recall the sphere here of genus 0 and the torus of genus 1 and so forth. And in general, the genus K surface can be obtained from the sphere by attaching K handles to it. So we'll use that later. So also in this talk, a cell structure on a surface will basically just mean a finite CW complex homeomorphic to the surface, where the images of each cell in the complex will be referred to as the cells in the surface. And so since we're talking about surfaces, we'll only have 0 cells, 1 cells, and 2 cells. The 0 cells will be a finite set of vertices. The 1 cells will be a finite set of edges that will join these vertices in various ways to make a graph. And then the 2 cells will be the rest, the faces in the complex structure. So basically, one useful way to think about this is the 1 skeleton, or the 1 cells and 0 cells, will form an embedded graph in the surface, and the complement of the this graph will be will have components that are these open cells, basically, each homeomorphic to an open disk. Some examples, of course, classically, the platonic solids are cell structures on the 2-sphere. Again, here I'm using the tetrahedral shell here. So if you blow air into it, this will be a cell structure on the standard 2-sphere. It would round out. And notice it'll have, of course, these 4 vertices at the corners and these 1, 2, 3, 4, 5, 6 edges joining them. And then there are these 4 triangular faces. So that's a very nice regular cell structure on the 2-sphere. And then over here on the torus, you can see a cell structure where the cells are these 4-gons, otherwise known as squares. And so notice this checkerboard pattern on the torus. And you can get that just by taking the standard identification of the torus from a strip of paper where you glue left to right and bottom to top and cutting a grid on that piece of paper. So that's a simple, example of cell structure there. All right, keeping going here. Now, to avoid some pathologies, we're going to look at things that are called closed cell structures. So in a general CW structure, the open cells are homeomorphic to disks, but their closures might not be disks. So we want to insist that the closures are homeomorphic to closed disks, and when that happens, we'll call it a closed cell structure. So the original 2 examples are closed cell structures. The closures of the 2 cells are basically homeomorphic to disk. But for an example that isn't, I'm sorry, this is so small. If you take the usual identification space of the torus, then you can put a cell structure on it with 1 vertex at the common corner, 2 edges, 1 for the left-right edge and 1 for the top-bottom, and then 1 single face in the middle. And that standard structure on the torus has 1 vertex, 2 edges, and 1 single face. The open box here is homeomorphic to open disk, but the closure is a torus. So that would be not a closed cell structure because the closed cell is not a disk. All right, so we're kind of looking mostly at closed cell structures going forward. All right. Now, like we mentioned earlier, there's one group of people that study cell structures through the cells, but when you're talking about 2 cell structures, often a different group, the graph theorists, would think of a cell structure on a surface as an embedding of the 1 skeleton graph into the surface. So for a given cell structure, let's say the tetrahedral shell, it makes a graph here with 4 vertices and 6 edges, and you can view that same cell structure as an embedding of that graph in the 2-sphere. And that's sort of equivalent. So they take that sort of viewpoint. Notice that in general, since the surface is connected and adding 2 cells does not change connectivity, in order to be 1 skeleton of a CW structure on a surface, you have to be a connected graph. So just that point here. This is just mentioning conversely, if you take a finite connected graph and embed it in a surface such that the components of the complement are open disk, that will define a cell structure on the surface. So basically, there's a one-to-one correspondence between cell structures on a surface X and the cellular embeddings of finite connected graphs into X. So tessellation people will usually think about cell structures, but graph theorists would usually think about embedding graphs into surfaces. So for example, the famous Kuratowski theorem basically tells you which connected graphs can embed into the plane or equivalently the two-sphere and so forth. So you can try to look at which graphs embed in which surface and think about that. In general, if you take the graph theory viewpoint, a finite connected graph Y has a minimum genus G min where it embeds in a surface of that genus, and then a maximum genus G max where it embeds in the cellular way into that surface, into a surface G max. And it turns out one can prove that the graph will embed in every surface of genus G between its minimum genus and its maximum genus. So there are no gaps. So if you can embed in, let's say, genus 3, and you can embed in genus 10, then you can embed in all the genuses between it. And so that's a general fact from finite graph theory. Now, it is known to be very hard to compute the minimum genus that a given graph embeds into, and that's some NP hard computation, but it's known to exist. We won't need so much of that today. All right. So regardless of how you think about these cell structures on surfaces, sorry, tell me if I'm going a little too fast through some of these. I'm happy to slow down.
John, let me interrupt you and ask the question. If you go back a slide,
sure.
I've just never really heard of the maximum genus before. So, yeah. I mean, a lot of graphs, do they have, I guess they don't have maximum genus infinity because it wouldn't be a closed cell structure that you could build on top of.
That's right.
I see.
So what you're saying is very important. Like if I didn't insist that we were talking about cellular embeddings where the faces were open disks, then you could take an embedding like the tetrahedral graph here in the sphere, and you could attach handles in the interior of the face and get arbitrarily big genus.
Right.
So the reason that we can't get arbitrarily big genus is the requirement that the faces, the open faces, are disks. Because if you allow the open faces not to be disks, like in a CW condition, then you can attach handles in the middle and there would be no maximum genus. But when you do require the open disks, open cells to be disks, that's enough already. You don't even need to require the closed cells to be disks, just the open cells have to be disks. Then you can show there is a maximum genus. Like I say, it's less important and not less used. The one genus people usually hear about is the minimum genus.
And is the maximum genus also in some cases hard to compute?
Actually, it turns out that one is actually easier. I believe there's a polynomial time algorithm. And a great book on topological embeddings of graphs in general into surfaces is this book by Tucker and Gross. And that's kind of one of the main sources that really talks about things beyond the minimum genus. Like most graph theory books talk about the minimum genus. Right. In like Gross and Tucker, they talk about the maximum genus and the fact that you can, there's no gaps in the genus that you can embed in all the things in between.
That's fantastic. Thank you. Yeah.
All right. Yeah. So please do ask questions. If not, I'll try not to zip through slides too fast. It's kind of first time online here, so I hope I'm not doing the annoying thing of zipping through too fast here. But basically, we're going to look at cell structures. There are many, of course, types of cell structures you could get. Like, if I plop down a bunch of points in the plane and take the Voronoi cells, I'd get a cell structure on the sphere. But those will generally be irregular. So we are interested here in cell structures that have a high regularity, at least combinatorially. So to talk about that, we'll introduce the automorphism group of a surface cell structure. And that's going to be the subgroup of homeomorphisms of the surface back to themselves, so self-homeomorphisms of the surface that take cells to cells. So the automorphism group will be the homeomorphisms of the surface that take vertices to vertices, edges to edges, and the faces to faces. So basically, they're permuting as sets the vertices, the edges, and the faces. And we won't elaborate too much. For us, our cell structure will be mostly regular. It'll be pretty clear what a cell automorphism is. But that's going to be an important concept. And then to one form of regularity we can insist on is a cell structure can be called vertex transitive if this automorphism group acts transitively on the vertices. And that, roughly speaking, has the interpretation that every vertex is at least combinatorially similar to any other vertex in the structure, in the sense that the number of edges incident to it, the local the number of faces that it touches will be always the same. Of course, the existence of the automorphism means that this symmetry is global, but that's what a vertex transitive structure would be. And then similarly, we could ask for edge transitive structures and face transitive structures. So for example, if a structure is face transitive, that would imply all its faces use the same number of edges in it. So if one uses edges or is an n-gon, then all of them would be if it's face transitive. Finally, we asked for the most you could ask for. So a cell structure is regular if its automorphism group acts transitively on flags, where a flag is a vertex inside an edge inside a face. And so to say it acts transitively in flags would mean that if I take one flag, V1 inside of E1 inside of F1, and another flag, V2 inside of E2 inside of F2, then there's some automorphism that takes the first flag to the second. So everything will be really very transitive. So this implies, in particular, individual vertex, edge, and face transitivity, but it basically says the placement of any flag is pretty much the same as any other. So a high form of regularity. An example, as most of you would guess, are the platonic solid structures on the sphere. Those are highly regular, but there'll be more, and we'll discuss that in a bit. In the cases that your structure is regular, then all the faces will border the same number of edges, which we'll denote by n, and we'll call these faces combinatorial n-gons. Now, it's important here that I only require homeomorphisms to act. So that means you don't really need that each face is isometric to another face. You just need a homeomorphism that can distort the face, in non-important ways. So it's a sort of combinatorial equivalence. So again, even though I don't draw it, we're talking kind of combinatorial equivalence today. So these structures that I drew pretty regular here, you could make the edges curves if you wanted to in this discussion. I'm sorry, I shouldn't have done that. All right, oops. Now, in a regular structure, every face will be an n-gon, and then every vertex will lie in the same number of faces, which we'll call the valency of that vertex k. And to kind of keep this sane, we'll collect that data in what's called the Schläfli symbol, nk. N is for the face type, and k is for vertex valency of a regular structure. All right, so enough rambling here. Let's look at some examples. I hope that wasn't too much. Oh, there's a little more rambling here. I'm sorry. For a regular cell structure, there's some important arithmetic connections. First of all, the Euler characteristic of the surface of genus G says for any cell structure, number of vertices minus number of edges plus number of faces is the Euler characteristic, which is 2 minus 2G for a surface of genus G. In a regular cell structure, if each face has n edges, then each face contributes n edges towards the total. But it's easy to check that every edge lies in two faces in these structures, in these closed cell structures. And so that leads to NF being 2E. And then similarly, every face, since it's an n-gon, contributes n vertices. But since every vertex touches k faces, k is the valency of a vertex, that causes NF to be kV. So the regularity gives us these relationships between face and edge counts and face and vertex counts. The Euler characteristic gives us this. So as you can see, very constrained, and it'll turn out, we'll mention this later, for a surface of genus bigger than or equal to 2, there's only a finite number of possibilities for all of this. For genus 1 and 0, there are some infinite families, which we'll discuss basically right now. So let's look at some examples. So the tetrahedron, let me just check on time here. Okay. The tetrahedron, being a platonic solid, easily can check it's regular. 4 vertices, 6 edges, 4 faces. Each face is a triangle, so n equals 3. And each vertex touches 3 triangles, so k equals 3. So that's the tetrahedron. Now, if we looked at the dodecahedron, that's its info here. Again, each face is a 5-gon, and each vertex touches 3 5-gons. So Schläfli symbol is 5, 3. All right, sorry, stop me, I was zipping through. Here's one you don't see usually listed because for triangulations, you assume every face has at least 3 edges in it. But this is a fine CW structure, basically a beach ball or a sliced orange or lemon. And that's called the hosahedron. And the hosahedron has only 2 vertices, one at the north and one at the south pole. And you can see you could slice this into as many pieces as you wanted. And so the number of edges can be an arbitrary n. And you have the same number of faces as edges in this. So this is a hosahedron structure on the 2-sphere. Again, each face is a 2-gon, and each vertex, the only 2, touch n faces, so the valency is n for the vertex. Now also, although I didn't get a picture for this, in general for a cell structure on a surface, there's a dual cell structure where you put a vertex in the middle of each face, and then you draw an edge between the center vertices of each face when the original faces share an edge. Now, in this case, what happens when you take the dual of the hosahedron, unfortunately, I didn't write it here, you get the cell structure on the 2-sphere where you have n vertices on the equator, n edges on the equator, and 2 cells, one the northern hemisphere and one the southern hemisphere. So that's also regular. And by the way, when you do the dual of a regular cell structure, the Schlafly symbol inverts. So that one would have 2 n cells, and the vertex valencies would be 2. So it would have symbol n2. All right. For variety, let's go up a genus. So that square mesh on the torus was a regular structure. Each of these were 4 gons. Again, you can see, and this is basically because the Euler characteristic of torus is 0, that most of the regular patterns on a torus are scalable. So you could take the standard identification of the torus as the rectangle with the sides glued and cut a rectangular mesh on it with m rows and n columns, or s rows and t columns, and get torus with st faces. And here we just said n faces, and it turns out number of vertices is the same as the number of faces. So since each is a 4-gon and each vertex touches 4 of these faces, its Schlafly symbol is 4, 4. And you can easily show every composite n it has a structure like this. Now, even when n is not composite, if you get a little creative, you can make a square mesh on the torus with 5 cells. And here is an example of that. So if you look carefully, remember the top and the bottom are glued in the torus, and the left and right edge are glued. And you'll see there are 5 cells and 5 vertices in this structure for the torus. So a square mesh with 5 faces for the torus. All right. Okay.
And so is this one also scalable here?
It gets a little trickier when you have non-composite, but you can put all, by using suitably sloped lines, you can actually get, I guess any number of cells. But I guess it's not scalable in the sense that I'd have, as if I scale the size of the torus. Sure. I can, for any torus, find the right slope that this would work out as. Yeah, I guess I'll say it that way.
Thanks.
But yeah, we'll maybe get back to that later. Now, unfortunately, the construction we talk about won't just have regular cell structures, but ones that are pretty close. So I'm going to also have to talk about those. So let's now talk about a little less regular structure. So there's a notion of quasi-regular, and this is dual to that, hence the horrible name dual quasi-regular. So a cell structure is dual quasi-regular if the automorphism group doesn't act transitively on full flags, but on partial flags of edges and faces. So for any edge in any face, E1 and F1, and any other edge in any other face, E2 and F2, there's an automorphism that takes the first pair to the second. So in dual quasi-regular structures, it's edge-transitive and face-transitive, but not vertex-transitive. So since it's face-transitive, the faces will still all have the same type. They'll still have all the same number of edges in them. But it's only face and edge-transitive, so it might not have one orbit of vertices. Now, if you think about it, because it's edge-transitive, and any edge can be moved to any other edge by an automorphism, any vertex can be moved to one of the 2 vertices on some reference edge. So in this sort of structure where it's edge-transitive, there can at most be 2 orbits of vertices. And so in a dual quasi-regular structure, we might have to break up the vertex set into 2. So V breaks up into V1 and V2. where the vertices in V1 have one valency lambda 1 and the vertices in V2 have another. So that will just be a slight minor complication, but most of the things go through no problem. So the vertex set breaks up into two types of vertices. Euler characteristic still holds. Face edge relationship still holds because they still have the same regularity. And then for the vertices, now there are V1 vertices of valency lambda 1 and V2 of valency lambda 2, so you get the slightly modified equation. But it's still true for genuses bigger than or equal to 2, these four equations cut you down to a finite number of possibilities. So these are still relatively special structures on surfaces. Now, the Schlafly symbol for this sort of dual quasi-regular cell structure will have an N for the face type and then list two valencies for the two different types of vertices you have in it. So let's look at some examples. Well, for the sphere, one example is the so-called rhombic triicontahedron. Here, the faces are all foregons, so it is face transitive, so all the faces are these rhombus. But you'll see that some vertices, like where my mouse is here, have valency 5, they touch 5 faces, and some have valency 3. So this is an example, it's edge and face transitive, but there are two orbits of vertices, the ones that touch 5 faces and the ones that touch 3. So foregone faces and these two valencies, 5 and 3, is the Schlafly symbol. All right, so now just to give you an idea of what's out there, let's list the regular and dual quasi-regular cell structures on the sphere. Now, this is a list of all the ones where the faces involve at least 3 edges. So unfortunately, for various reasons, our construction later will always make faces with at least 3 edges. So we bullied the hosahedron, and it's not on this because it has 2 gone faces. So this only lists 3 gone faces and higher. And so basically, there's that dual hosahedron with the all the vertices and edges along the equator and those 2 cells. Here, when we double something, doubling is just the process of taking a cell structure and subdividing each edge into 2 edges. So when you subdivide each edge into 2 edges, you multiply the type of face it was by 2 and introduce some new vertices. Let me give some other example here. So for example, the tetrahedron had triangular faces and every vertex touched 3 triangles. When you double the tetrahedron, i.e. subdivide the edges of the tetrahedron, the triangle faces technically become 6 gone faces because now instead of having 3 edges in a face, you have 6. And the vertex valencies, when you subdivide, there'll be the subdivision vertices that have valency 2, and the original vertices will have the original valency. So one dumb way to get a dual quasi-regular structure is to take a regular one and subdivide it. So that's not so interesting. So you'll notice here there's some regular structures, and then we doubled them, and that's just their subdivision. So those I don't view as really that interesting. But there are some genuine new dual quasi-regular structures on the sphere, which are the rhombic dodecahedron and the rhombic triicontahedron we saw earlier. But the rest of them come from regular structures.
And if I tried to create a quasi-regular structure from a regular structure by tripling or quadrupling an edge, I'd fail because it'd no longer be edge-transitive?
Yeah, that's right. It won't be edge-transitive once you do too much more. You'll get more orbits of vertices, and you know if it's going to have a chance of being edge-transitive, there can at least most be 2. So I've hidden all those details, but you can't subdivide more than once. That's right. And you have to be regular to start to have a chance.
Right. And this is the complete list here.
This is the complete list of all the structures with faces at least 3 gons. I threw out there's some silly ones. You can actually use a 1 gon consisting of a single simple circle in the plane, the sphere, the plane, complex plane with 1 vertex and 1 edge, and then you have 1 gon faces. So I've thrown out those cases and the 2 gon faces from the lemon slices. So other than that, though, it's complete. This was just because later we won't need those at all, so sorry about that. All right, and then similarly, you can do a similar thing for the torus. Again, these are the regular or dual quasi-regular structures on the torus that have faces that are at least 3 gons, so no 2 gon ones are listed. Here, the 6-3 one consists of basically the hexagonal packing of the plane, where you tile the plane by hexagons. And then you can notice you can cut that off and make a torus out of it. And you can use as many hexagons as you want. Well, you can do many examples depending on how you cut off the torus. So this is the hexagonal tiling, if you will, of the torus. And then if you subdivide the hexagons into triangles, triangulate them, you would get this one, this 3, 6 one. So this is triangulation of the plane / torus. It's a periodic one, so you can do either. Now, amongst these, this 4 is the square mesh on the torus, and these doubles are just barycentric subdivision cases again. So the only interesting one for the torus is this 4, 3, 6 one, which luckily I could find a graphic for. So here's the so-called rhombic star tiling. It's actually, this picture is for the plane, so it's actually a little bad for the torus, but it will work. I'll tell you in a second. And if you look at this picture, first of all the cells are fourgons, and some cells, like where my mouse currently is, touch 3 fourgons, and some cells, like this one, touch 6. So 6 and 3 are the 2 valences. Now, this tiling doesn't quite work because they cut it off wrong here, but if you make a vertical line right here, you'll see that you can make a periodic tiling on the torus. So you just have to crop it a little bit to get one for the torus. So anyway, that's this tiling of the torus, or this structure on the torus. And that's it. So that's for the torus. And then for higher genus, I'll just say that if you specify the data, the genus, number of vertices, edges, faces, face type, and vertex valences, then for any genus being equal to 2, there's only a finite number of possibilities for the data. And people have classified the possibilities up to genus 15 for the regular case. Dual quasi-regular can be done, but I don't think has been done, but close enough. So just to say what's out there. Okay, so given all that, that's to prepare you what these sort of regular or quasi-regular structures are. Now I'd like to discuss this sort of group theory construction that associates to any finite group a collection of surfaces with this sort of patterns on them. And this construction will basically encode the non-commuting part of the group multiplication table. It'll be equivalent to this. So let's take a look at that. So now we'll start talking about the construction of surfaces and regular patterns on surfaces from group theory. Now, prior to this, there have been a lot of constructions of this historically using things like triangle groups, Fuchsian group actions on the upper half plane, branch coverings of the sphere and lifting patterns from the sphere to other surfaces, and various other constructions. And this one just adds another to the pile. This one has the benefit that it comes canonically from a finite group, and that finite group will basically act on the collection in a very natural way. And so what this particular construction did was yield a lot of examples of interesting group actions on these pattern surfaces that had questions for other reasons. People are interested in looking at groups acting on surfaces, and these kind of help do that. When we did this construction, at first, we described our construction. It took a while with other experts telling us how to fit it in with the standing literature, so I hope I'm doing a reasonable job here. But anyway, now I'm going to outline how we can use a group to construct surfaces with these patterns on it. To be non-trivial, for the remainder, G will be a finite non-abelian group. So always non-abelian finite group. All right, so let's talk about this construction. So first of all, we're going to make a simplicial complex from the group in the following way. So the vertex set will consist of 2 types of vertices, and each type will be labeled by the non-central elements of the group. So central elements are elements that commute with everything else. Non-central elements don't commute with at least one thing. So we'll take 2 copies of the non-central elements, and this second label is just a formality. So I equals 1 or 2, just 2 copies of each x non-central. And then we'll define this two-dimensional simplicial complex where the maximal faces or facets will encode a multiplication of x with y, where x and y don't commute. So the 1 slots represent the 2 inputs, x1, y1, and then the output will the 2 slot will represent the product, xy. So let's take a look at a picture. Also, by the way, we'll order or orient this triangle using this ordering: left input, right input, output. So here's a typical picture. So for two non-commuting elements in the group, x and y, we just label them x1, y1. This triangle represents the product of x times y, so to equal xy. So x, the 2 just indicates it's the output slot. The orientation is from left input, right input, output, so we get a left-hand orientation here. Now, when you look at this complex a little more carefully, a few interesting things happen. If I look at one input and one output specified, and if I now say y should be the left input, there's a unique right input such that y times that is this, and that's from group theory. So basically, you can argue for every edge between a type 1 and type 2 vertex, there's going to be exactly two triangles that are adjacent to the edge, one where y plays the role of the right input, and one where it plays the role of the left input. And since we're only putting in triangles when things don't commute, it's easy to check, well, what this thing here is y inverse xy, since y times y inverse xy is also xy. And this is not equal to this when x and y don't commute. So basically, the way we've defined it is these triangles represent the group multiplication table for non-commuting products, and every edge here will be in two triangles. Furthermore, you can check the way we're orienting things, the orientations cancel along this edge. Now, the same thing works for the edge between two type 1 inputs. If I have x1, y1, well, they don't commute, so they're going to be part of two triangles, one where x is the left and right is y is the right input, so xy, and one where y is the left and x is the right, yx. So a long-winded story, this complex is defined this way from the group multiplication table, and it has a nice property that every edge in the complex lies in exactly two faces, and the prescribed orientations of those faces cancel along that edge. All right, so, and I'm lazy here, we didn't write, we should have drawn more. This is only a few of the triangles. So basically, main thing is every edge has two triangles in it, because specifying two inputs gives you two possible outputs since they don't commute. And giving one input and one output gives you two triangles depending where the input's the left or the right input. All right. Now, if you were an ant living on this simplicial complex, oh, by the way, another thing is if you have any vertex, since it's a non-central element, we're only using non-central elements, it won't commute with something, so it will be part of one of these edges, and therefore part of one of these triangles. So this simplicial complex is the union of these specific triangles encoding the group multiplication table, or at least the non-commutative part of it. Now, if you're an ant on this complex, if you're in the middle of a triangle, there'll be a neighborhood of you that's an open disk, so you'd think you're on the plane. If you're in the relative interior of an edge, since each edge lies in two triangles, there'd also be an open neighborhood that looks like the plane. So as far as an ant on this weird complex would be concerned, away from the vertices, it looks like you're in the plane locally. So it's a two-manifold away from the vertices. So let's take a look what happens. So again, every edge lies in two faces. For another thing to mention is this complex is compact and connected. Compact is just because we only have a finite number of triangles, because the group was a finite group. To see it's connected, if we go back here, by definition, every triangle has an edge between two type 1 vertices in it. So to show the whole complex is connected, it's enough to show the graph induced by the type 1 vertices is a connected graph. And to see that, just notice if you have two non-central elements, the things that commute with, oh, these should be small x's. The things that commute with small x will be a proper subgroup since it's non-central. And so at most, half the things in the group will not commute, will commute with x. Because the centralizer of x is a subgroup and it'll index at least 2. So at most, half the things in a group commute with x. At most, half the things in a group commute with y because they're non-central. But identity commutes with both of them, so there's a thing in common here. So if these each have at most half size and have something in common, they are going to be strictly less than the group. And so given two non-central things, there's always something else that doesn't commute with either of them. And if you look at the definition of our complex, that means there's a path from x1 to y1 through z1, because we draw an edge between two one-type vertices exactly when they don't commute. And so basically the diameter of that graph's at most 2. Finally, just before I get into the ramble here, the group will act on this complex through simplicial automorphisms by conjugation. And that's because if you conjugate everything by an element alpha, that doesn't change. The conjugate by alpha of x times the conjugate by alpha of y is the conjugate of xy by alpha. So the whole complex is preserved under conjugation. So you get a conjugation action of the original group on the complex. Here, we're just repeating the point that an ant not at a vertex would think that it's on a manifold. Now, at a vertex, here's a picture. Here's a typical two vertex, an output vertex. X and Y have product XY. Now, since each edge is shared by exactly two triangles, this edge here is shared by another triangle, which you can compute has this vertex. Then this edge of this triangle must be in another one. So you can keep proceeding where each edge, since you know it lies in two triangles, you can find another triangle that extends each edge. And this has to keep going until you come back to where you started because of finiteness of the whole setup. So again, since each edge is inside exactly two triangles, when you take one of these reference triangles, it'll make a sheet of triangles around this midpoint. And so if you look at what can happen in general for a given output, let's say alpha 2, it could be a product of many distinct things, like alpha could be A times B, it could be X times Y, and it could be U times V, and these might be in different sheets. So the typical picture around a vertex is that of a bouquet of disks, if you will. So these are like triangulated disks, each coming together at a single point. So basically, you definitely get singularities at vertices in general. The ant will know it's not on the plane if it's at this vertex. The same sort of picture can be shown to occur at a type 1 vertex. I won't torture you with that. So you do have these vertex singularities. So basically, at this stage, the upshot is one can prove that from the non-commuting part of the multiplication group of non-commuting part of the multiplication table of a group, you would get a singular surface that's compact and connected, where the pieces outside of the vertices would look like manifolds, but at the vertices you could have sheets come together like this. And one can show it's actually like this. It's like a singular manifold, if you will. So the only singularity is at the vertices, where the link of a vertex might not be one circle, but more than one circle, as more than one sheet comes together. So like over here. So the link of this vertex are these three circles here. And it should only be one if it was really like a manifold. So it's a singularity. All right. Oh, my God. All right. I'll get through here. So the upshot is, what do we do when something is a manifold outside of the vertices? Well, you could take the finite number of vertices out. So take the finite set of vertices out. Now, each vertex was labeled by a group element, x1 or x2, where x was some non-central group element. So you could take out all the vertices, at which case the ant no longer has any objections. Every point that's left looks locally like the plane. And so you have a punctured, collection of two manifolds, which you can show have a finite number of components now, no longer connected after you take out the vertices. You'll have a finite number of components with punctures in them. But after you take out a point, let's say this was labeled by group element X. After you take it out, these punctures still have that label. So what could you do? You could just say, well, after I take out X and I have these punctures that came from X, I'll put in now, in this case, 4 different copies of X and replug in the punctures. So after, you play this mind game of taking out the problem vertices, so now it's a manifold with punctures, and then you put them back in, but instead of having 1 copy of X1, you might now have 4 copies. But if you do this, one can check that it doesn't ruin that these are triangulated surfaces. And the only thing that happens in this desingularization process, where you took out the vertices and put multiple copies in, is that you still have a triangulated collection of surfaces labeled by group elements. And the only thing that might happen now is a given element might occur more than once in the collection. So X1 might occur in 4 different vertices now. Notice in this process, the edges don't change at all and the faces don't change at all. Only vertices have been added. So it doesn't change face or edges at all. Okay. So the upshot is you end up with what we call YG, the desingularization of the original thing XG. And this is a finite set of triangulated, closed, connected manifolds. Now, I should have said this earlier, but the fact that the orientations canceled on the edges, along the edges, implies that these manifolds are orientable. So after you do this from any non-abelian finite group, you'll get a finite collection of closed orientable manifolds. And they basically, if you maintain all the vertex labelings from the group, encode the group multiplication table. So you might as well say it's equivalent to the non-commuting part of the group multiplication table. All right, so now these are triangulated surfaces so far, so not so interesting patterns on them, just triangles. This just repeats all the ramble I was doing. So this YG construction is a finite collection of triangulated surfaces from any non-abelian finite group. Together with the vertex labels, it is clearly equivalent to the non-commuting part of the multiplication table because those triangles were literally telling you the multiplications. The group acts simplicity on this complex by conjugation. You can check the action goes through the desingularization process. And again, desingularization didn't change triangles and edges, but only vertices. All right. Now, for future reference, we want to pick out one of the components. You get a lot of surfaces, so let's have notation for one of them. So for two group elements that don't commute, there was an edge in the construction because they don't commute. X1, Y1 was an edge lying in a triangle with XY2 as the product. This edge wasn't changed during the desingularization, so it lies in a unique component surface in that construction, which we'll call YXY. So that just picks out one of these surfaces. So if the edge XY was here, then this surface would be YXY, and not those would be thrown away. All right, so now last bit, just to kind of get to the point. Finally, we're going to make a cell structure on these surfaces. We got the surfaces with triangulations on them. We're going to get the cell structure by suppressing all the type 2 vertices and any edges touching type 2 vertices, and only keeping the type 1 vertices. So the output vertices are going to be dumped just from the cell structure, not from the surface. So let's see if I can get a picture here. So that's going to be this MXY. Let me just do it through the theorem. So the main theorem is that after you do this, the surface that you get will now have a cell structure that's either regular or dual quasi-regular. So it's a very nice structure. And here's a picture that might help. Don't read this ramble here. So here was the original triangles in the triangulation. Here's X1, Y1, and then the product XY2. We've suppressed the index 1, so the input index we've dumped, just for simplicity. So X, Y, and then the product. So the 2 here index is a product index. So when you have this triangulation, each of these sheets is made out of all these triangles. You're going to throw away the type 2 vertices and all the edges joining it, and now the face will be this n-gon. So this round cell here would be a cell in the final structure. So the triangles were used to build it, but the cell in the final structure will be just the type 1 vertices on the rim. Type 1 vertices, the edges between them on the rim, and then the cell inside would be that circular region. All right. So the upshot is, and now that time's running short, maybe I have to leave on the paper. I'm sorry, oh my God, all the examples I'll just zip through. Is using the group conjugation action, you can show that by suitable conjugation, the action of the group acts by homeomorphisms on the structure, and by suitable conjugation, and that's in the paper, it takes any face to the face adjacent to it. And so all faces in a given surface have the same type. And then using the conjugation action, you can show that it's face and edge transitive. I'm sorry, just rushing through that. So maybe just to rush through some examples here quick. If you did this for the dihedral group with 8 elements, you end up with 3 octahedra in the original triangulated complex. Here are the inputs and the outputs. Vertices have the 2s on them. But after you suppress the output 2 vertices, the cell structure you get, let's say on one of these, would look like this. You'd only have the 4 vertices and edges on the equator and the 2 cells on the north and south pole. So one of those dual hosohedra. Not so interesting here, but just to give you an example, so 3 dual hosohedra would be the dihedral group on 8 letters. The quaternion group on 8 things happens to be NC isomorphic to D8. So they're not isomorphic groups, but the non-commuting parts of their multiplication tables agree. Apparently that can happen, so there's nothing new there. This construction only sees that part. So they also 3 octahedra. But as you look at other examples with P groups that are higher, you get lots and lots of interesting structures. Since unfortunately time ran out, I apologize, I went too slow earlier. I'll just give you one typical example. A typical finite group will give you lots of structures and tell you how to build them. So I'm going to pop out here. Unfortunately, we don't have time to go through these here. And I'm going to give you just a table for a typical group.
Oops, looks like we lost John momentarily, but now he's back.
Sorry, I couldn't send that.
No
All right.
worries.
All right, just going to quit one table and then I'm done. I'm sorry about that.
No worries at all.
Just so you can see in a typical example. So a typical example, even a small group like A5 has like thousands of surfaces it manufactures. So it's ridiculous. You need definitely computer help in general. Sorry, just going to pick out one table and then we're done here. Table was in a different. Come up here and I'll share this. All right, we're nearly there. So sorry I didn't get too many examples, but basically upshot, every finite group's non-commutative part of multiplication table is a bunch of tessellated surfaces. Here's an example for, this is ridiculous, this one. So, okay, for A7, it's ridiculous, but let me just do it. Alternating group on 7 letters. You end up getting 16,813 surfaces. Genus 0 has a bunch of them. You'll notice here amongst them the tetrahedron, the cube, dodecahedron, and icosahedron. But you get lots of different genuses with different cell structures, and it's ridiculous. So I'm sorry, just to show you the idea. So these are all for the same group A7. But the main thing about this construction is it's coherent for the group. So the group acts on all of these and gives you symmetry groups for each of them. And it gives you lots of examples of interesting group actions on these surfaces. And that was the point of the paper. But anyway, just I think that's it. Thank you all for your patience, just to give you an idea of how group theory might connect with tessellations. More details, of course, are in this paper, which appeared 2 years ago in topology and its applications. Thank you once again. Sorry.
Thanks so much, John. So before we ask questions, please go ahead and unmute yourself if you're quick enough on the draw. And let's thank John. Wonderful. So any follow-up questions for John? John, I had a question. So
Sure.
When you go back and try to match these surface components with the non-commuting parts of the groups, how direct can you make that that translation? You know, can you start to understand how different surfaces, say, of different genuses are related to the different properties of the group?
Yeah, definitely. And the paper does talk more about that. So basically, if you maintain the vertex labels, of course, the group's still there and there's no difference. So if the vertex labels were there, that were the original group labels, that basically encodes the group, the non-commuting part of the group. So up to NC isomorphism, you get the group back. But once you forget the labels, of course, and just have the tessellated surfaces, it is a little tricky to go back, but it definitely tells you about structure of the group, the groups. So, for example, the odd order theorem, I believe that every odd order group is solvable, which everyone would say, sort of has their favorite way to say something's equivalent to it, would be equivalent to every simple group having a surface of genus 0 in its bevy of every non-abelian simple group having a genus 0 guy occur in its bevy, for example. But generally speaking, they do encode like these subtle, group theoretical point invariants. In fact, you can use the group action on any of these surfaces to get faithful action of subquotients of the group on each individual surface. And then the so-called group cohomology of that subquotient is readily related to the surface genus and things like that. So definitely a lot of indirect invariance. It's a little tricky, of course, long story short, to directly relate. It's kind of a mess. But for example, central extensions of groups yield branch coverings of the corresponding surfaces. And through all this, you can show that every surface we get, after you mod out the whole group action, you will get a sphere. And so you can show that each of these surfaces ends up being a branch cover of a sphere with 3 branch points. And that was a relatively special situation that actually people in this theory had used before, starting from that end. They basically look at 3 branch covers of the sphere and lifted patterns from the sphere to other surfaces. And these branch covers that a branch over 3 points are specifically important because the theorem of Belyi tells you they represent surfaces defined over Q bar. And so long story short, this was done by Grothendieck, of all people, for various things to help study, help construct these pattern surfaces as a way to study the Galois group of Q bar over Q, it turns out. And so there's a lot of rich study between Galois groups and actions on these pattern surfaces. And that theory falls under the so-called Dessins theory. And so as the final thing, we start from a different end and in the end show that you end up at the same spot they did. So we don't get anything new that they did, but we're starting from an elementary side, whereas they start from the branch covering and go backwards. So it's kind of, anyway, so in terms of how it fits, but it's still complicated. The group theory is there, but hidden in some various complicated ways.
And another question I had, so this dual quasi-regular structure, this is coming from dualizing
quasi-regular. Yeah, so quasi-regular by the name means vertex and edge-transitive. So quasi-regular is vertex and edge-transitive, but the faces are not transitive, so you can have different types of faces. A good example is most soccer balls, I think, have a quasi-regular structure. Where you'll see that they have some hexagonal and some pentagonal faces. And so the dual of quasi-regular is dual quasi-regular. It's basically whether you pick on vertices and edges versus edges and faces. But ours just happens to work with edges and faces. So, but yeah, understanding one is equivalent to the other. So those classifications earlier are kind of equivalent to the duals of the quasi-regular structures.
And is there a version where all the vertices are sort of transitive and all the faces are transitive, but the edges are not?
Okay, like I think that probably. Oh, okay, that's a good one. I'm just trying to think here. I'm just blanking here suddenly. So you have face transitively. So all edges are equivalent to something in a face, and then so maybe the same. So yeah. So if your vertex sorry.
Oh, go ahead.
Yeah, okay. Let me think about that and get back to you. But yeah, good question. I think somehow no, but I'm having there's a notion of arc transitivity that might come into play, whether you can map an edge to itself if without specifying the vertex that's in it so that you might have to do a flip. But anyway, let me come back to you on that. I'm sorry, don't really know that. I'm like a amateur in the area that had to be told all these things 2 years ago, but people totally liked it. But
Any final questions for Jon? Well, thanks so much for a fantastic talk.
Thank you for having